Okay, this is part 2 of chapter 3. In this lecture, we will go over the last about third of this chapter, and it's regarding the least square line. I don't know if you remember from the previous lecture. In the beginning, we were talking about how visually providing, uh, uh, how visually describing data, specifically when you have two quantitative variables such like uh, income and years of experience. In that type of situation, we could plot a scatter point plot. Okay, and it would look something like this. We would plot this in a coordinate system. Okay, and we would measure one of the variables on the y-axis, another on the x-axis. Let's have this as wages, and this be years of experience on the job. And we would probably see something like this if we plotted the points. We would see the data like in an upward sloping kind of relationship. What that basically means is that as the years of experience goes up, likely the wages of this individual goes up. And that probably makes sense. The more years of experience you have on the job, likely you're going to get paid more on average. Now, from here, I don't know if you remember from the previous lecture, we inserted a quote unquote trend line. We use Excel and we figured out how to insert this trend line. Okay. What we are going to do in this lecture is we're going to estimate this trend line. We're going to figure out how Excel created this trend line, and we're going to figure it out ourselves. Just basically figure out what the y-intercept would be. Remember, this is a line. So the formula for this is y equals mx plus b. Y is the wages in this case. X is the years of experience. M is the slope. And b is the y-intercept. Right here, this is our b. The slope is like this, rise over run. So this is our b. And I'm going to provide you with the formula necessarily to estimate your own trend line. Okay, so let's move on. We'll clear this. All right. Well, on a side note, we will learn a lot about this towards the end of class. We're going to go over the last 2 chapters, or maybe just the last one, OLS regressions. And this is basically your quick introduction to OLS regressions, the least squared line, section 3. Okay. Now we're going to have a couple of assumptions. We're going to assume that we have 2 variables. They're quantitative variables, x and y. And we're going to assume here that the y is the dependent variable and x is the independent variable. Okay. That is something that we need economic theory to provide us, which is the dependent, which is the independent. Right now, we're going to assume y is the dependent and x is the independent. Okay. And here's some example. The cost of a home may depend on the amount of floor space. The larger the square footage of a home, all else held equal, the home value will increase. The student's GPA may explain his or her score on the achievement test. Yes, a student who is quote unquote doing better in class is likely to do better in the SAT on average. And the individual car type owned may explain his or her income. So someone who maybe drives a Corolla maybe makes less money than someone who drives a Porsche or a Ferrari. Okay. Now, it doesn't always have to be true, but on average, that likely is true. All right, so let's move on. Okay. So our least square line, okay, when we have a dependent and an independent variable, it's going to look like this. Y is equal to A plus BX. Okay. This is no different than the equation I put up 5 seconds ago or 5 minutes ago. Y equals mx plus b. The only difference is we're using A as the y-intercept instead of b, and we're using b as the slope instead of m, okay? So this is the least square line, y equals a plus bx, where a is the y-intercept, b is the slope. And remember what the slope tells us? Okay, well, first let's do the y-intercept. What does the y-intercept tell us? The y-intercept tells us what is the value of y when x is 0. That's what the y-intercept tells us. So when x is 0, the value of y is a. What does the slope tell us? It tells us the movement in y when x moves by 1 unit. For every 1 unit increase in x, what is the movement in y? It's b. So let's say if b is, say, 3, then for every 1 movement in x, y will jump up by 3. If b is -1, then for every 1 unit increase in x, y would fall by 1. Okay, so the b tells us how y moves when x moves by 1 unit. Okay, again, if b is positive, y increases by b. If b is negative, then y decreases by b when x changes by 1 unit. And if b is equal to 0, there's no relationship between x and y. And in this situation, the line will be horizontal. Okay, so here's a least square line. I've already kind of explained to you this is A, and for every 1 movement, we go up by B. Again, for every 1 movement in X, we go up by B. And this right here is the least square line, where this is the formula. All right, let's move on. Okay, so in an ideal world, all the data points land on this straight line. But we know we don't live in that world, and we need to quote unquote fit a line between a cloud of points. Okay. When a scatter plot of 2 variables, x and y, are created, the points usually do not fall exactly on a straight line. So we have a situation like this. Okay. Let me scroll up a little. Oh. Situation like this. We have an x and we have a y. Point A, point B, point C, point D, point E, point F, point G. So we have all these points, and what we're going to do is figure out the formula of the line that fits through the points. Okay, it's kind of like drawn right here. So what we're going to do is create this line, okay? And what we're going to do is define a y with the little thingy on top. This is called y hat, or that's the way I call it. And that is going to equal a plus by. What do I mean by that? If we have some value of x, okay, So let's say right here, we have some value of x right here. Okay. So x is I don't know, 0.7. Okay. This is the point that we're going to have y right here. It's going to be 2.5. So the data of that point is right here, a. Okay. That is the data. It's like right here, a. That's our data. Okay. And x is 0.7 and y is 2.5. Okay. So a. All right. So this is our y right here. This is equal to y. But what we're going to do is create a line, this blue line, and y hat is right there. So it's a little below 2, above 1. What is that, like 1.8? So this is y hat is our estimate, or you could say a forecast or prediction of y given our formula. So this is quote unquote our model to find or guess or forecast y. Okay, this is the model we're going to establish to kind of forecast y. That's what a linear trend line does, is it tries to forecast y given we have x. Okay, and a and b is our quote unquote model parameters. That's basically our model. Okay, we get some input x, which is our independent variable. We multiply it by b, and we add an a, and we say that's our best guess of y. So y hat is our best guess of y, basically the y that's on our trend line, and y, the true value, is right here, 2.5. Okay, so let's first figure out the formula to find our guess of y, and that is right here. Okay, b, which is the slope, that is equal to the correlation coefficient times standard deviation of y divided by standard deviation of x. Let me read. Of y divided by standard deviation of x. Okay, so that's what b is. Given we found b as this gobbledygook of a number, correlation coefficient multiplied by standard deviation of y divided by standard deviation of x, we could find a. Once we find b, step 1 is to find b, and then step 2 is to find a. A is equal to y bar minus b over x bar, where this is the average y, and this is the average x. So you get the average of all the y's in our data point minus b that we found here times the average of the x's in our data. Okay, so what we're going to do now, given that I showed you how to do this, what we are going to do is example 3.7, where we're going to apply this formula on some real data. So what is the data? This is the data right here. Okay, so let me just punch in the data into Excel. Data. We have an x and we have a y, and our data points are 2, 3, 4, 5, 6, 7. Oh, 7. And our y is $8. Okay, $9.50, 10, 14, 15 and 1750. And let me put in the decimals so it looks nicer. Highlight everything. Click on this button here to increase the decimals. Increases the decimal. So this is our data. We have some X's and some Y's right here. Okay. And so what I'm going, oh, okay, the formula is right here. So what we're going to do, and here's the answers, is what we're going to do is create our model for this best fit line, which is y hat is equal to a plus bx. B is this gobbledygook. A is this gobbledygook. Okay. So what they tell us is that y is the starting hourly wage rate. So let me just put that in here. Okay. Wages, starting wages. And x is the number of experience on the job. Experience years. Okay. Let me just note that so we know what it is. Okay. All right, so let's do this. So we got B is equal to correlation coefficient times standard deviation of y divided by standard deviation of x. So in order to solve for B, we need the correlation coefficient. And we also need standard deviation of x, standard deviation of y. The correlation coefficient in Excel is CORREL, CORREL, open parentheses, put in your first set of data, either X's or Y's, it doesn't matter what you put in, comma, put in your second set, so it doesn't matter if you put in X first or Y first. Just put in your data, close parentheses, there's a correlation coefficient. Standard deviation of x, the formula is equal to STDEV dot, and this is a sample. So we're going to do S for sample, open parentheses, put in your x's. 2, 3, 4, 5, 6, 7, close parentheses. For your y's, STDEV dot S, open parentheses, put in all your data, close parentheses, enter. All right, so now your B is equal to R, correlation coefficient, times the parentheses, standard deviation of Y divided by standard deviation of X, close parentheses, and there's your B, 1.94286. Yeah, 1.942. What? Oh, these are rounded. That's why. Close enough. This is the non-rounded value. All right, so A. In order for us to find A, well, we need the average of Y minus B times the average of X. So we need average Y, average X. So let's calculate these. Equal to average, open parentheses, put in your Y's, close parentheses, 12.33, equal to average, open parentheses, that's the formula. Highlight your X's, close parentheses. Okay, just because we want to make it pretty, we'll highlight everything. Maybe use, no, too many. 2 decimals? No, let's just keep it at 2. Okay, so what is our A? A is equal to average Y minus, and because I'm paranoid, I'm going to put a parentheses, B times average X, close parentheses. I like to group them in a parentheses to make sure they are done before they get subtracted. Enter. 3.59. All right, so we know our B, we know our A. So now let's create our formula, which is Y hat is equal to A plus BX. x, right? Let's make sure that's what our formula is. Y hat is equal to a plus bx. So let's write out the formula. Okay, so what I'm going to do is I'm going to put right here an x, and I'll say this is my x. I'm gonna put a yellow little box. That's where I'm gonna put my x, and I'm gonna say y hat is equal to a plus b times, okay, and because I'm paranoid, I'll put a parentheses around these guys, x, which is missing right now, close parentheses. All right. So if I put because it's missing, it's equivalent to setting x to 0. So let's put 0, see? And right now with x equal to 0, b times x disappears, so y hat is just equal to a, okay? So why did I do this? Because I could put in any value of x, and then y hat will change instantaneously. For example, if I put in 1, changes to 5.5, 2, 7.48, okay? Let's put in 0. So again, this is why I do this. And now let's figure out, what did we just create? What is y hat? Well, remember what y is. That is wages. So we had data on people. Let's say person 1. Hold down the control, scroll over. It goes 1, 2, 3, 4, 5, 6. We have 6 data points: person 1, person 2, person 3, person 4, person 5, person 6. And we have their data of how many years of experience they have and what was their starting wage given these years of experience. And we use this information to create a formula for y hat. And remember what that y hat is. It's our model to estimate wages given we have x, or number of years of experience. We found that the slope is this, and we found for our model the slope is this, and for our model, our linear model, the y-intercept is this. And what this means is so that given we have our formula, if you put in 0 years of experience, the person's starting range is estimated to be, starting salary is or wage is estimated to be 3.59. So let's say your boss is the HR manager at a company. You created this model, and your boss is like, okay, we're gonna hire somebody who has 14 years of experience. Can you give me an idea what we should pay this person? So what you would do, assuming this model is reasonable, you put in 14 for your X, or the years of experience, and Shazam, your model says, that person's starting salary should be about 30.79. Well, what about someone with 7 years of experience? It should be 17.94. Note that it's 17.19, I mean 19, $17.19. Note that it's less than 17.50. Again, we use this data to create our model. 1719 is the number that's right on the line. 1750 is the actual data, which is up here. Okay. Here is the model. Here again is for 7 years of experience. 1719 is on the blue line. 1750. So right here on the blue line, let's be right here, 1719. The red dot is actually 1750, which is slightly above. Okay, so basically this is the end of the lecture on this chapter. Here, the last bit of this is how to calculate correlation coefficient. We've already went through this is just a summary of how to do it. We've already went through this. Here's again a summary of how to calculate the regression line or the least square line. Okay. And this concludes the notes for the second part of chapter 3. Okay, have a good night.